most prestigious tournaments, earning a record $3.2 million.
Ladies and gentlemen, Brad Rutter. And now our next player.
In 2004, his record-breaking 74-game win streak.
Ken.
Who's Aristophanes?
Ken.
What's the Trojan horse?
Ken.
Who's Jean Lafitte?
Ken.
What's the dodo?
Ken.
What is Stella?
It's just acne.
So there have been 2 world champions in Jeopardy. They have been winning millions of dollars, and never could, nobody could beat those. And now,
It's the Trojan horse.
then
It's just acne.
I mean,
You
what's
don't
the
have
name?
this skin infection, also known as Hansen's disease. Watson,
What is leprosy?
you are right.
Badgered brute for 1600.
Music fans waxed rhapsodic about this Hungarian's transcendental etudes. Watson,
Who is Franz Liszt?
you are right.
Don't worry about it for 1600.
You're just a little stiff. You don't have this painful mosquito-borne joint illness with a Swahili name. Watson,
What is dengue fever?
dengue fever, correct.
Badgered brute for 1200.
Paganini's 24 Capricci set the standard for etudes for this instrument. Watson,
What is violin?
good.
2000, same category.
From 1911 to 1917, this romantic Russian composed Etude Tableau for piano. Watson,
Who is Rachmaninoff?
Rachmaninoff is correct, and that adds to your lead. You're at 13.
okay, so I think you got the point. Then we had some announcement that IBM Watson is outperforming different sorts of humans. And then I wanted to show you something else. Have you seen YOLO before? It's not all, okay. For those who haven't.
So this is 10 times faster than the 20 seconds per image detector. And you can see that by the time it makes predictions, the entire state of the world has changed. And this wouldn't be very useful for an application. If we speed this up by another factor of 10, this is a detector running at 5 frames per second. This is a lot better. But for example, if there's any significant movement, I wouldn't want a system like this driving my car.
Okay, so be prepared for YOLO. This is faster now. Then we have, I think from last year, a model which can extract 3D representations of persons from 2D video streams. Okay, so the message is that the area of deep learning and AI is highly in research, and every 2 weeks you have a new paper and can try out something else. And therefore, it's not that you have a black box which you can just deploy and run. You need something more open, like my NAS at home from Synology, which is based on open source technologies. And if I want to tweak it, I can even run Docker images on my NAS and get the hard drives out and connect it to my Linux box and read the contents again. And that's the message which we have here in the IBM Cloud. So we want to support all the open source frameworks as good as possible. And we do that in IBM Watson Studio. And that's the thing I'm constantly using to show you. It has some sort of components. So you have black box services as well in Watson Studio. For example, visual recognition, which is an image processing service which you can create also with your own data. But if you want to open the black box, then you can use Watson Studio notebooks and deep learning as a service. Here are some other services. If you need a database, also you can pull from there. So it's Jupyter and RStudio, and the compute environments, they are elastic. The idea is we have a free here, which is 2 CPUs and 4 GPU of RAM, where you can sketch your algorithm, and if you recognize that you need more, for example, it takes 1 day to train, then you have a drop down and you select other CPU and GPU configurations, and then you pay per hour. Yeah, and then the more closed source services like visual recognition, or we have a neural network designer which can import and export Keras, TensorFlow, Caffe models, and some data integration tools and so on. But that's beyond the scope of today. So I just wanted to, I mean, that's cool, that's the deep learning as a service. So you can configure a hyperparameter grid, and then the service automatically runs all those parameterizations in parallel. It tells you about accuracy, and then you select the best model. So that's something I tended to do in nested for loops, where I just took one parameter in each hierarchy, but it's something which you can automate, and also the resources are then deployed for you and then are also deprovisioned. So each task, each hyperparameter point in the hyperparameter hyperspace is then one experiment which gets one Docker image which runs on Kubernetes, which then gets a number of GPUs assigned, and then that's something you can configure. That's the example you asked me. So we have one other hardware stack, which is Power AI, and here are some world records, for example, in scaling efficiency and runtimes and accuracy. But I will skip over that as well, because you are here for something else. Just let me see. Yeah, maybe one interesting thing which currently is in discussion is how do I exchange models. So there's PMML, predictive model markup language, which usually isn't enough for expressing all the sophisticated topologies. And the new runner-up is PFA, portable format for analytics. And the idea is that you have built-in language in the specification where you can express your linear algebra. Therefore, it makes model import-export portable. And our idea is that we support all the different standards like Onyx and Neat and even Pickle and Emily, PFA and PML. Anyway, okay, that's what I mentioned. Fabric for deep learning is the whole stack which we are using for hyperparameter tuning and so on as open source component. And I think I stopped from there. And then, one last thing. We have this Coursera specialization, which, so I'm showing you slides and material from the AI, applied AI with deep learning. But for those who want to know more about, for example, Apache Spark data integration, visualization with Apache Spark is the first course, or the second is the whole ordinary machine learning pipeline and also signal processing. So in what's an IoT, we do a lot of signal processing, and then you do a capstone where you prove that you actually can solve data science problems, and then you get the official IBM and Coursera certificate. So that's enough. The URL is openai.ai/data science. So now let's do one thing. I haven't seen all the hands raised when I asked the linear algebra question, and I just wanted to show you one thing which changed my life in linear algebra. It's not this one, it's not scalar multiplication, it's the vector dot product, because when I started my career in that space, this was 2010-11, I forgot about linear algebra, and I was reading papers, and I saw WX in the publication. I had no clue now way to understand what those guys mean with WX. So this is how it works. W and X have been vectors, and if you multiply them, you get back a scalar. And that's, if you don't know it, you have no chance in understanding that publication. So here you see one vector and another vector and the multiply symbol, so that's the dot product. And if you want to multiply two vectors, you just multiply the first component of the first and the first component of the second, with each other, and you go on with the other ones. And then you sum up all the individual components, and then the result is a scalar. Okay, that's I think the only thing I wanted to show, or maybe one other thing. Yeah, you can do the same with matrix and vector, of course. But I wanted to show you one thing. So this is the generic form, and for those who don't know, this is the same as linear regression. If you take x as the data points and a as the parameters, you can express linear regression with two vectors. And that's also part in every neural network. So the first compute step in a neural network is always a linear regression step. So, and that's basically all I wanted to show. No, that's I wanted to show. For those who don't know what a tensor is, even vector or scalar or matrix is a tensor. So a tensor is a data structure of arbitrary dimensions. And if you have, for example, here 3 dimensions, you have 3D tensor, a matrix is a 2D tensor, a vector is a 1D tensor, and a scalar is a 0D tensor. Okay, then because that's the reason why they call it TensorFlow. Okay, so I assume I don't have to explain to you how a neural network works. So are you familiar with the perceptron? Okay. So can you tell me which part of this perceptron is the linear regression part? Yeah, so this is basically this part. Does everybody see that, or is somebody not seeing that? Just tell me, because I'm now basing all the subsequent talk on the assumption that you every. Hi, Florian.
Hi.
So did you get that?
Yeah.
Okay, good. So so this is then you have the activation function, and interestingly, if you put sigmoid here, for example, you get a logistic regression. And if you put a step function here, you get a perceptron, and if you put any other activation function, you get a neuron. So this is it, and now let's go to the convolutional. I have seen also many hands raised when I asked for the convolutional neural networks, and therefore I will also do it fast. So image classification is the most prominent example for convolutional neural networks. Have you heard about the universal function approximator theorem? Yes, no, okay. So this says that a single hidden layer neural network with an infinite number of neurons in the hidden layer can mathematically approximate any function. That's some magic theorem. There are some catches because the word infinite, but it's doing pretty well. So that actually means, in theory, if you want to create an image classifier, you need just to take each pixel as one input feature and then use a single hidden layer neural network and the number of output classes, so you are predicting an output vector. And then in theory, since the universal function approximator theorem tells you that this neural network can represent any mathematical function, this should be a very, very good model. But it doesn't tell you, so it tells you it's you need infinite number of neurons, so that's a bit fishy. But the other fishy word is represent. Okay, that means it's not saying it can learn. So learning or training this universal function approximator is your problem. So that means finding the parameter matrices W is your problem. And today we don't have efficient training algorithms. We are still stuck with gradient descent, unfortunately. Anyway, if you want to do image recognition, we are not allowed to use spatial information. Therefore, we do convolution. So convolution, who doesn't know what convolution is? Okay, so convolution is basically applying one function over the other and getting a result. It's some sort of a filter. So this is a 1D convolution where the black line is the result of convolving G over F. And this is the same example for a 2D input space. So this is a monochrome image, as you can see. It's me. Just the resolution is a bit, no, just kidding. It's 0 and 1s. And so that gets considered this as an image. Okay. Normally you have 3 channels, here you have only 1, and normally you have values between 0 and 255, for example. I think it was 16-bit, for 8-bit to color them. So then now comes the trick. You convolve another matrix over the first matrix in the following fashion. So you are doing that in strides. So you since this convolution matrix is smaller than the input matrix, you have to convolve over it. Okay, so you start top left, and then you have different strides. For example, 1 by 1. So you shift 1, 1, 1 to the right, and you can walk 1 down, and so on. So what you do is here is you take the input, the subset of the input, convolve it. It means if you have a 1 at both matrices, then you put also 1 in the output. If there's a 0 in the convolution matrix, you put a 0. So it acts as a filter. And then you are pooling. That means you are taking that result and you count the number of ones, and then you put it in the result. Okay, that's how this goes. And then you get the final result. And the trick here is you are learning the convolution matrix. So the values of the convolution matrix are updated during training. So that's part of the optimization objective. And this is a famous image and from a 4-class image classifier, where after training the activations of different layers have been visualized. And at the bottom you see the first layer. There are 2 things you should see. Can you try to tell me what 2 important things you see?
Let's see.
They're the same, yeah. Second. Yeah.
So first, filters of the convolution layers, just find the edges of the
Yeah.
basic
Yeah. There are no
filter.
concrete shapes. It's only very basic lines, circles, and rectangles. And this is in total accordance to the visionary cortex of mammalians and most likely also insects. So the way how they found this out is they opened the scalp of a cat, a bit cruel, no? They put the electrode into the visual cortex of the cat, and they've shown the cat a line, and they turned it, and then they changed the distance, and at a certain angle and a certain distance, a specific neuron was firing. So they discovered that in the first layer of the visual cortex of mammals, we also have these filters. That's interesting, so we are copying the biological brain here. Then pooling, I will just skip. There's usually those neural network topologies get really big, between 50 and 150 layers. You usually always have a convolution and then a pooling layer. So you are just downsampling, but you preserve the spatial information. That's always important. In convolutional neural network, in 2D convolution, you preserve the spatial information. Yeah, that's basically it from, let's say, layman's terms perspective. And then, okay, the message of this slide deck is that there exists a huge variety of recurrent neural networks, but I'm only using LSTMs extensively. LSTM stands for long short-term memory networks. And so we already learned, until now we have the universal function approximator, which can do some magic. We learned that training neural networks is hard and inefficient, especially also from a resource point of view, but especially from an accuracy point of view. So there are better parameter assignments for your neural network than you can find with gradient descent. But anyway, we have the universal function approximator, but it's still a function, and the function per definition doesn't have state. It's stateless, so for any given input vector you get always the same output vector, which is nice for image recognition, which isn't that nice for sequence data, like IBM Watson IoT sensor data streams, or natural language, or audio streams, or whatever, okay? Or stock market data, whatever, okay? So the neural network is dumb, it can't remember anything. So the solution to that is to put a memory cell into the neurons. So this here is a LSTM neuron, and at the same time it can also be a LSTM layer, because as you have learned in the linear algebra piece, it doesn't matter whether you are computing on scalars, on vectors, or on matrices. If you're computing on matrices, you are just computing a whole layer in one go. That's pretty good. So that doesn't matter if we talk here about a neuron or a layer, but for simplicity, this is now, let this be a neuron. So it starts as usual with the input data vector xt, and as usual with the downstream result vector of ht. And as usual, you have an activation function. So you have a mapping between xt and ht, but in this case it goes through ct indirectly, and I will show you how. So there is an input, an output, and a forget gate in an LSTM neuron, which control or act on the cell state. And you see here, what goes into the cell state is also squashed down in the activation function, but in addition, the input gate also learns from the same input data some sort of how important this data is at this point in time. And then here is a valve, and which can be opened and closed. And based, so it gets even more interesting, based on the input data, based on the actual cell state, the input gate decides how much of the actual data it wants to remember. Okay, that's the first thing. Second, based on the input data, based on the actual cell state, it decides how much of the actual cell state it wants to send downstream to the downstream layers. And finally, based on the input data, based on the actual cell state, it decides how much of the actual cell state it wants to remember or wants to forget. Okay, so we have done some magic, and we have no chance of understanding that. Okay, so how this now leads to such a cool neural network, which is Turing complete. Okay, so if you have a LSTM layer in your neural network, you are having a Turing complete model, meaning that again in that universal function approximator theorem, which can represent any mathematical function, a Turing complete neural network can represent any program or software which a von Neumann architecture can execute, or which a Turing machine can execute, which is pretty cool, pretty scary. But again, there's a catch that's only talking about representing and not training. So if you can improve training in machine learning and deep learning, then you are the king. Representing, we can represent everything. No? So that's the question so far.